All right, subscribers, welcome back to another episode of Science with Surbeck. Today, what we're going to be talking about is Chemistry 1, Section 16.4, and this deals with calculating enthalpy change. So before we get going in the video, a couple of objectives I want to outline that you should be able to accomplish at the end of these notes. So objective number 1, use Hess's law of summation of enthalpies of a reaction to calculate the enthalpy change for a reaction. Objective number 2, explain the basis for the table of standard enthalpies of formation. Objective 3, calculate delta H of the reaction using thermochemical equations. And then objective number 4, determine the enthalpy change for a reaction using a standard enthalpies of formation data. So we start out here with Hess's law. Now, Hess's law, what it is going to state is this. It states that if you can add two or more thermochemical equations to produce a final equation for a reaction, then the sum of the enthalpy changes for the individual reactions is the enthalpy change for the final reaction. So kind of a mouthful there, so I'm going to pause and write that definition down. All right, so there is the written definition. There's a lot going on. There's a lot stated in this definition. But the major thing here is it's saying, hey, we know this delta H for one reaction. We want to manipulate it to be able to find the delta H for another reaction. So the best way to learn about Hess's law is to really do an example problem. So down here it says use the thermochemical equation below, these equations below, to determine the delta H for the decomposition of hydrogen peroxide. Before we get going and we get to manipulating these equations, a couple things I want to point out. Number one, this guy right here on top, this is known as the desired equation, and it will always, this desired equation will always be given. So I'm going to put that in parentheses. You're never going to have to come up with an equation on your own, but this given equation will be listed out here on top. And notice on this top equation, there is no delta H. That is our job with Hess's law, is we need to go find delta H. So what we have down here are two equations that if we add them together, and we're going to have to do a little bit of work before we get to the point of where we can add them together, we can be able to come up with this equation. And then on the flip side here, we can add together the equations plus the delta H's. Now, what we have to do is we have to make our equations, the equations that we are given, we have to make them look like this. And that's the part that we have to use our knowledge of Hess's law through this example. So in our desired equation, I start out here and I look for something that is similar or for something that I need on this left-hand side. So I stop here and I see, hey, I need two H2O2s. So what I do first is this. I go to my given equations that are down here below, and I see, hey, I have H2O2, but it's on the wrong side. So what I need to do with this is I need to flip the equation. So all I'm going to do to indicate that I'm going to flip the equation is I'm going to switch sides. So I'm going to literally take this stuff that was on the products and now make it a reactant. And I'm going to rewrite that as H2O2 as a liquid. We flip it because that again, we flipped everything of this equation. So now our H2, the H2 gas is on the right-hand side, and the O2 gas is on the right-hand side. Now, that's great that we flipped it and that we matched this part right here, but what we need to do now is we need to flip the sign of delta H. So a positive becomes negative, a negative becomes positive, and this is because we flipped the equation. So we look here at delta H, and this was negative 188 kilojoules. Because we flipped the equation, the delta H becomes endothermic, and it becomes a positive 188 kilojoules. Now, once I've rewritten this, what I like to do is this. I like to cross out the equation that I have used so that I don't confuse going forward or confuse myself going forward. So right now we have H2O2, which is on the left, which matches up exactly how we want it over here with our H2O2. And now what I want to do is I want to make sure I have the right number of H2O2s. So if I look here, I only have one H2O2 in this given equation where I know delta H. So what I actually have to do is I have to multiply everything by 2. So when I multiply everything by 2, what I end up getting is this. I end up getting 2 H2O2, yields H2 plus O2. Now, I messed up here. We have to multiply everything by 2. So it's not just H2, it is 2H2. And it's not just O2, it is 2O2. Now, because I multiplied everything in this equation, I also have to multiply this by the same number I did over here. So now I have delta H is equal not to positive 122, but doubling that particular number. So I'll pull out my calculator here and calculate that. All right, so what I have here is I'm just going to take 188 and I'm going to multiply it by 2 because I multiplied that whole equation by 2, and I end up, again, still with a positive 376 kilojoules. Now, again, once I use a particular equation or once I manipulate it like I did up here, I get rid of it so I don't confuse myself. Now, the next thing I look over here, I need H2O on the left-hand side, and I need 2 of these H2Os. So this equation right here where I have my pen is that exact equation. Now, I don't need to do anything to this because it's on the correct side, and if you look closely here, it already has the correct coefficient. So all I'm going to do is with this top equation is I'm going to write it down below. So all I'm going to do is a copy paste, and I'm going to have 2H2, which is a gas, plus O2, which is a gas, yields 2H2O, which is a liquid. And then because I did not manipulate anything here, I can obtain, or I can keep this same exact delta H value, which is still negative 527 kilojoules. So now comes the double checking. What I'm going to do with these two equations is this. I am just going to add them together, and I'm going to do a couple of things before I just add them together. Number one, if a substance, the same substance is on one side of one equation and the opposite side of another equation, I can eliminate them, or I can, in math, they call that canceling out. So I look here at our first thing. The first thing that I notice on different equations on the opposite side, like H2, again, different equations, they're on opposite sides, that same substance. I can reduce two H2s with two H2s. So when I do that, I can actually eliminate our H2. Now, I keep looking throughout this, and I don't see anything that directly cancels, but this oxygen can be reduced. So I have two O2 on the right up top, and down here I have only one. So what happens is this will simplify, this will cancel out, this one will cancel, and so this one right here, instead of 2O2, I canceled it with this 1, so I end up with 1. I'm just going to have that serve as a reminder. Now I double check before I go through anything here. I double check to make sure there's nothing else that can cross out. There isn't by just glancing at this. So what I'm going to do here is I'm just going to add whatever is not crossed out and make sure to have the correct number, the correct coefficient. So all I do here is 2 H2 O2, which is a liquid. Yields are 1 O2 plus our 2 H2O as a liquid. Now, what I'm looking for is this equation that I just wrote here in green should look very similar, should have the same reactants and same products and same coefficients as what we have here. So I had 2H2O2. Down here I have 2H2O2. Over here I have 2H2O. Now, I have 2H2O. It is okay that it's on the far right side. As long as it's a product, it matches out with this. Now, O2, I only need one O2. Over here, I have one O2. And again, just because it's closest to the arrow, it doesn't matter as long as it's a product like we have in our desired equation. So this check right here works out. This should match this equation up top. That's our first check. If those two things match out, all we need to do is we need to add together our delta H's exactly how we have it listed here. So in this case, what I'm going to do is I'm going to take my positive 376 and I'm going to add it, to negative 527. And so the delta H that I obtain for this decomposition of H2O2 is negative 151 kilojoules. Now, we got Hess's law. This is a big part of the problem. The next section, or the next portion of this section, deals with something we've already looked at. I just want to jump into some more details. So I'll change pages here, and we'll get started with page 2. All right, so with the standard enthalpy of formation, this is a problem, or a similar type of problem that we have done. I just didn't make a couple things clear in that particular process. So number one, with our standard enthalpy, what we're finding is the enthalpy change under standard conditions. So standard conditions are as follows. Standard conditions, there are two things. Number one, we are at 1 atmosphere, ATM, of pressure. And then number two, we are at 25 degrees Celsius. Or if we're working with Kelvin, this is 298 Kelvin. The other thing that is true with our standard enthalpy, of formation, is this. This is forming one particular mole of a compound. The additional thing I want to write down here is the symbol notation. So the symbol notation that we use is delta H with this little circle. So this little circle that we have written down here, what this means is it says, hey, we are at standard conditions. So if you ever see that, that means, hey, we are at standard conditions. And then the other thing is this. We have a particular formula, which I didn't make very clear, but our formula for this, our formula for standard enthalpy of formation is the reaction, the delta H of the reaction at standard conditions, that little circle, is equal to the sum of the number of moles, which I am going to indicate by our N, multiplied by the standard enthalpy of formation. So in our standard enthalpy of formation, what we are going to get is our delta H of F. This is all for the products minus, and I'm running out of room, minus the N, which is moles, times the delta H of formation of the reactants. And I always squeeze that in. Now, a couple of things to note. Number one, the N, this is going to stand for our moles of a substance. The delta H, this is something we can look in a chart. So now we get down to our example problem. We want to know what is the standard enthalpies of formation to calculate the change of enthalpy at standard conditions. That's what that little circle means for the combustion of methane. So always remember products minus reactants. So we start out here. Our delta H of our reaction is equal. I always put a bracket. And then I start out here with a parentheses, and I start out here with the coefficient, which represents the number of moles of CO gas. So I have 1 mole of that CO gas. And then if you look in that handy dandy periodic table packet that I gave you at the start of the year, and it's always available, this one right here, and you turn about 3/4 of the way, you will see a bunch of values here. Now we are dealing with carbon monoxide that is in the gaseous phase. So on this, we are going to find carbon monoxide at the gaseous phase, which is negative 110.525. So I'm going to take my 1 mole and I am going to multiply it by this negative 110.525, and the unit on that is in kilojoules. It is in kilojoules per mole. Now this little symbol up here says add everything together. So that means I have to take the other product that is involved. So I have 2 moles of H2O, and we have to be careful here. H2O is a liquid. So if you look on the chart, you'll notice there's a couple H2Os. I want the H2O for a liquid, which is negative 285.83. And again, that is in units of kilojoules per mole. Now, I'm running out of room here. What I do here is this. I subtract all of this business by the reactants, products minus reactants. So I start here with the coefficient of CH4, which is 1, which means I have 1 mole of CH4. And again, I'm looking for CH4 as a gas. So I go to my handy dandy chart and I look CH4 as a gas is positive 74.81 kilojoules per mole. So I write down, I'm sorry, you can't see this here, but that is a negative value. The printer did not do a very good job there, but this is negative 74.81 kilojoules per mole. Again, the printer, I have an old copy here, that should be negative. We add together, because that is not the only reactant, we add together 2 moles from our O2. We put 2 moles, and we look up O2 as a gas. So O2 as a gas, if we look on our chart here, O2, we find O2 as a gas, and that is 0 kilojoules per mole. So we write down 0 kilojoules per mole. Now, calculations. There's 2 ways to do this. You can add everything in one and then subtract it from everything added together in the bottom, or how I'm going to show you is you can just do it in one simple calculation, but you have to be very, very, very careful that you put in everything into the calculator correctly. All right, so in the calculator, what we have to do, I'm going to start out with a double set of parentheses, and then I'm going to put 1 times negative 110.525. I'm going to close the parentheses, and then I'm going to add this 2 times negative 285.83. So I'm going to go 2 times negative 285.83. Now I close with a double set of parentheses because I end with a bracket. Now I subtract from this a double set of parentheses because bracket and parentheses, 1 times negative 74.81, and then I add to it the 2 times 0. Double set of parentheses because that is the bracket there, and I press enter. So for this process to happen under standard conditions, we get delta H of the reaction, and I added that circle because we're at standard condition. We get negative 607 kilojoules. So this means a couple of things. 1, it's exothermic, and 2, in a combustion reaction, because it's exothermic, we have heat that is released. All right, so this concludes section 16.4. I hope you've enjoyed another episode of Science with Surback.